Hi, thank you for coming. So I will be talking about the paper that was published last year in JER by Zohar Feldman, who was back then my PhD student. And the talk will be about online planning with Markov decision processes. In fact, what we discuss now applies to other more complex settings of sequential decision processes, but adaptations will have to be made. So while we will be talking about Markov decision processes, you can apply the same ideas to adversarial Markov decision processes, to partial observable Markov decision processes, and adversarial partial observable Markov decision process. Pick your nightmare. The basic objective in all cases will be to execute at the end a finite sequence of moves that visit good states. I will not repeat the definition of DP. I think that by now you know it by heart. Basically, we talk about planning with full observability and possibly stochastic actions. And rewards, which again can in principle also be stochastic, but we'll assume they are deterministic for a moment. So the challenge, while the basic MTP problem can be solved in polynomial time, it is polynomial in the number of states and the number of actions. Number of actions is okay, number of states not so in the problems that we usually deal with. An additional issue that affects the complexity, affects the computational challenges is that the model of the problem may not necessarily be given to us. It's quite often the case we have to deal with simulators of the actions and optimize our behavior using these simulators only. So we do not have access to explicitly described model. Now, if this is the case, within the scope of this problem, we'll be focusing on online planning. And let me describe what we expect in online planning, what we call online planning, because this notion by itself is a bit ill-defined. So, first of all, by online, we mean that we are currently at the state as 0, and we are interested in picking, in selecting action only for this state. However, when I'm saying picking action for this state, the long-term effects of this choice should be taken into account as much as possible. But we do not compute, not even try to compute policy for more than S0. Our interest is in any time algorithm in the sense that we do not know when the planning will be terminated. So the agent is asked to think, then it is terminated and has to execute some action. We're also striving, because of this limitation, to kind of smooth any timeless. So at least in theory, the improvement of our recommendation is smooth over time. So the jumps between time points in which we can guarantee some improvement of the recommendation will be short. And the quality measure under which we will be examining our work is what is called simple regret. But basically, it's too fancy name for a very simple thing. We think, we are stopped, we recommend an action, and so our regret is basically the difference between the goodness, between the value of that action and the action that would be recommended by an oracle, basically the best action at this stage. Now, Monte Carlo research became quite popular in the recent years, and when you put all the Monte Carlo research algorithms on the same board, you get this template. Basically, the algorithm loops. Within each iteration of the loop, it issues a rollout in the state space starting from state S0, with basically simulated execution of some actions for limited number of steps. This limit on the number of steps will be denoted from now on H. Then, having the information collected along this rollout, it updates its internal data structures. It can be a tree that is gradually grown by the algorithm, but the actual graph can be either tree or DAG or even a set of disconnected components. So nothing really precludes us from using non-tree Monte Carlo research algorithms. Once again, the agent is terminated and asks for a recommendation. The action that is recommended is the action that maximizes the estimated quality of the actions at state S0. That's it. Again, the rollouts are used to update information, and different algorithms maintain different variables at generated states and actions. The typical counters that are maintained are the estimated quality of action A when applied at state S with H steps to go, but also how many times we have visited state S with H steps to go, how many times we applied action A at state S, H steps to go, etc., etc. So counters and estimated quality of the actions. Now, different algorithms vary, well, there's not a lot to vary in this template, right? So they vary along two axes. A, how to issue the rollouts. And that induces basically what pieces of data will be updated. Two, the update strategy itself, because with the same information you collect, with the same target update, you may do different things and update things differently. One of the algorithms that became very popular, and I think that kind of is responsible for boost of MCTS in the planning community, is called UCT. It was introduced in 2006 by Coxis and Szabo-Sepeshvari. And it was the first algorithm that guarantees non-parametric convergence to optimal action at the current state. Again, there were algorithms that guaranteed convergence but were parametric. This one is not, almost. So here, let me explain you how it works. So there is a magic algorithm called UCB Alpha. I will elaborate about it in a moment. But so when we issue the rollout, and we are at the state S, we select action A prescribed by this procedure that I will explain in a moment. Once we select an action, we apply it, and we simulate, we use the simulator, so we end up at the next state according to probability distribution of the induced by the problem. And we stop the rollout either when we get to a dead end, where no actions are applicable, or we reach this horizon H. Having finished issuing this rollout, we now collected information, and we go now back along this rollout. We update all nodes along that rollout. We update these nodes with rewards collected down these states along the rollout. So basically with the sum of the rewards collected under the state. And how we update? We average. So all the samples that correspond to applying action A at state S are averaged together. This is what is now called the Monte Carlo backups. Average. Now, what is UCB Alpha? UCB Alpha is an algorithm that was proposed by our Cesabianchi and Fisher in 2002 for learning while acting in minimalistic MDP problems called multi-armed bandits. And basically, this magical formula, which is Chernoff bound made upside down, the algorithm does the following thing. I'm at a state S, and I should apply an action. If there is an action that I haven't tried even once so far, then I pick one of these. Otherwise, I tried all of them already, not necessarily the same number of times. Then I deterministically pick an action, ties broken this or another way, that maximizes the sum of two components. The first one is basically the empirical mean of that action, and that targets the exploitation part of the story. The second part basically captures our confidence in the quality of this estimated mean. Again, as I said, it's just Chernoff bound inverted. And it depends on the number of times the node was visited, which is the counter NS, and the number of times this specific action A was applied at that node. That's it. This is the algorithm. So, and this algorithm was quite successful, but it wasn't clear why. So when people analyzed theoretical property of this algorithm, kind of sad things popped up. First of all, the algorithm guarantees the convergence, but extremely slow. It basically guarantees only polynomial type convergence over time. Second, the initial period after which this convergence even starts can be extremely long, can be telescopically exponential in planning horizon. And that was proven by Coughlin and Munoz in 2007. So the question is whether we can do better. Again, UCT from some point on guarantees polynomial rate convergence, and this point in time can happen only very, very deep in planning space, time. The answer is yes, and that is the thing because of which you may consider reading the paper. The algorithm that I will explain in a moment called BRU guarantees from some point exponential rate convergence, and that point from which it starts providing this guarantee happens after only exponential in time horizon number of steps. You cannot do better. There is a lower bound for that coming from the work on sparse sampling. Now, how the algorithm works. Again, the blue parts are the important parts because they show the difference. The rollouts are issued not according to a fancy sampling policy, but simply according to uniform distribution. The catch is with how we use this rollout. So we issue the rollout according to this uniform distribution, and then we go back along the rollout, and at each state that we see, we issue an additional rollout. So if we're if we're I steps to go, then we issue a rollout of length I, according to expected best arm policy. So basically follow the best action so far. Collect the information provided by this rollout and use it to update the estimated Q function using MC backups. And that does the trick. The question is now, well, when you look at uniform sampling, I mean, surely, well, okay, maybe it buys you theoretical guarantees, but it cannot really be effective in practice. So more experiments in the paper, but here I will show you a couple of results on a specific planning domain that was used in the original UCT paper. The four algorithms that we put here just to show the differences is UCT, a variant of UCT that was examined by Tolpin and Shimoni that does basically UCT except for the root node, except for the initial state where it samples uniformly, BRU, and then just to examine to what extent these separate rollouts are important and uniformity are important, we basically generated a variant of the algorithm that samples not uniformly but according to UCT. But again, then, the updates are made by separate estimation rollouts as in BRU. Again, no heuristic is used and no other auxiliary tools that are popular in different communities, such as fast action, rapid function, rapid action value estimation, etc., etc. So here you see the error going down. So the simple regret going down over iterations. The complexity of iterations plus minus the same. And you see that the topmost graph is of, basically the top two graphs are variants of UCT. They start improving and then they typically oscillate. The third graph from above is this BRU damaged with UCT for sampling. And the bottommost graph is BRU, which surprisingly, even empirically, performs rather well on this domain. It is not always the case. If you have very short planning time, then UCT can give you better results, but that's not because it is good, but because it is lucky. Same phenomenon you can see when you increase the size of the problem. So here you can see that a variant that employs UCT is better at the beginning, but again, it loses this advantage very quickly, and that's consistent with theoretical analysis of Bubek and Munoz for simple regret minimization and multi-armed bandit problems. The only thing to take from this graph is the following. So the upper, the graph with the circles is UCT. The graph that goes pretty much in line with it is the basic Monte Carlo algorithm that generates no tree and just samples actions at the root and follows random policy from there on. So it's basically averaging over all possible policies in the space. You see that the difference is not that large. The BRU is the one that goes down from top to bottom, rather, well, goes down. And here I just want to show that you can do even better than that if you employ additional techniques, a reasoning technique about your problem space, think about variance, very careful with variance, and for that, there is a UAI 2013 paper that I suggest you to use by me and Zohar. I'm almost done. Bunch of other stuff you can find in the paper, including 30 pages of painful bounding inequalities. But if you want to prove something on Monte Carlo search on sequential planning, you will have to deal with this pain, because proving things about dynamic programming style backups is walk in the park comparatively to Monte Carlo on sequential decision problems, unlike simple multi-armed bandits. So summary, the kind of points to take. While UCT is a standard practice these days for online planning, things are changing, and in particular because there's no single argument for that. Two, in planning, unlike in learning while acting, which is a typical setup on reinforcement learning, nobody cares about exploitation. If something in your algorithm does exploit and you put it on your slide, know that you are doing something wrong. Because the only thing we care about is exploration. Now, you should think well how to do exploration in the problem in hand. So for example, if you look at the seemingly very different work of Nir Lipovetsky, Miguel Ramirez, and Hector Geffner on classical planning for Atari games, okay, you will see that what they do is think about how to explore well the problem they have. And UCT is losing there big time because it spends a lot of effort on useless exploitation. The last point, there are additional results also by both by Keller and Helmelt, and a few papers that we published on the subject that go and improve beyond BRU, at least empirically. And the last point is that a very big challenge remains online planning with contract setting. So not the setting in which you don't know when you will be stopped, but you actually know when you will be stopped. Now, you think, well, that should be easier, right? I know when I will be stopped. That should be easier for me to solve. No, because when you don't know when you will be stopped, the only thing you can optimize is the rate of improvement. When you know when you will be stopped, you don't care about improvements on the way, you care only about the result at the end. So basically you will be solving MDP just to think about your MDP. That's it.